Greetings and welcome to the Chemistry of Acids and Bases Separately lecture for Chemistry 223. We're going to go through a two-chapter kind of overview right now where we're going to look a lot at what acids and bases are all about. We've talked about acids and bases in previous chemistry classes. So like in Chemistry 221, we looked at basically how pH works, what an acid and a base is, but we didn't do a lot of detail. In Chemistry 222, we looked at carboxylic acids, and those are weak acids, as well as amines, the weak bases. But now in Chemistry 223, with our understanding of equilibrium, we can really get into a discussion of a wonderful source of energy for chemists, and the energy comes from the interactions with acids and bases. Sometimes the acids and bases are separate, sometimes they're together. We're going to look at the kind of techniques used to describe how acids and bases work. And we can't talk about acids and bases, of course, without referring to the pH scale. And on the right-hand side, that is a list of some common substances and their associated pH value. pH is usually a number from 0 to 14, but you can see there at the top, it can be less than 0. It can also be more than 14. Anyway, the pH scale is a quick way to tell if something is acidic or basic. pH of 7 is considered neutral, so pH is less than 7 are going to be somewhat acidic. pH is greater than 7 will be somewhat basic. And you can see a lot of common things on there. So there, for example, is coffee, which I'm drinking right now, big surprise. Anyway, coffee is one. There's seawater, ammonia, vinegar, all kinds of different things on there. So we're going to look a lot into this and how an understanding of acids and bases really helps us as human beings. So without further ado, let's get into this material. When you think about acids and bases, we do break them down into strong and weak categories. So you can have strong acids and weak acids, and you can have strong bases and weak bases. Strong acids are acids that dissociate 100% into hydronium and some kind of counterion. So this is an example of nitric acid, HNO3. When nitric acid is mixed with water, which it almost always is, you really don't have any nitric acid at all. You have exclusively hydronium and nitrate. And I want you to focus on the arrow symbol right there. After our discussion of equilibrium in the last section, you might think this is an equilibrium, but strong acids, we will use the single arrow, and that just implies that all reactant is converted into product, and all strong acids and strong bases, for that matter too, dissociate 100%. So if you had 0.1 molar HNO3 solution, you would actually have 0.1 molar hydronium, H3O+, and 0.1 molar nitrate. There wouldn't be any HNO3 running around. So strong acids and strong bases dissociate much better than the weak acids and weak bases do.
When a few drops of water are added to solid calcium hydride, a violent reaction occurs that produces hydrogen gas.
If you're dealing with a strong acid or a strong base, the reactions are quite pronounced. All right? That's a hydride there, and hydride, when they react, oh man, there's a lot of energy given off. Scientists use acids and bases, like I said, a lot of times just for their energy properties. They convey energy to different things, and we'll look at this more in this area. I do want to point out again the hydronium ion. All right, hydronium ion is H3O+, and that's going to be something we're going to talk about a lot in this chapter. Hydronium is the hallmark of an acid. So acids will create hydronium if they're going to be acids. We're going to see that bases will create hydroxide, but acids give hydronium. So make sure you remember that.
When nitric acid, HNO3, encounters a water molecule, it forms an acidic solution by donating a proton, the H+ ion, to the water to form a hydronium ion and a nitrate ion.
So hydronium forms from acids. The acidic hydrogen in the acid gives up to water and it ends up making this hydronium. Hydronium, we're going to see, is what makes acids acidic, all right? And we'll see that. Remember that with acids, almost always the acidic hydrogen is listed first. So HNO3 tells you it's an acid because H is listed first. That's not all the time the case, but I'd like it to be. But anyway, most of the time, if you have an acid, acid, the acidic hydrogen, is listed first. There are 5 strong acids, and I highly recommend that you memorize them / put them in your calculator or whatever you need to do. There are thousands of acids, but really there's only 5 strong acids that you need to worry about. These are 5 strong monoprotic, which means they give up 1 H+. And the 5 strong acids are nitric acid, HNO3, hydrochloric acid, hydrobromic acid, hydroiodic acid, and perchloric acid. And those 5 acids are very strong, all right? They dissociate 100%. We will use the single arrow when we're describing their reactions. We're not going to use equilibrium. That means that 100% of those acids will break down into hydronium and whatever the counter ion is. You're going to see that if you know these 5 strong acids in Chem 223, then all of the other acids you'll run into basically will be weak acids, and that can be kind of important. So I do recommend you know / memorize those 5 strong acids. Weak acids are much more common than strong acids, and a weak acid is weak because unlike the strong acids, which dissociate 100%, most of the weak acids don't dissociate 100%. And a common example we talked about in Chem 221, and we'll look at again here, is acetic acid. Now, acetic acid, for whatever reason, is a lot of times abbreviated HOAC. OAC minus is the acetate ion. Acetate is one of the polyatomic ions we've been dealing with. But anyway, acetic acid plus water does have hydrogen transfer to make hydronium, and you have some acetate, but this is going to be now in equilibrium. All right, you won't have all of the acetic acid breaking down to hydronium, and usually it's much less than that. So roughly, if for acetic acid, it's like 1 of every 10,000 molecules will make hydronium, but the other 9,999 will stay as molecular acetic acid. So there's not the driving force for making hydronium in a weak acid that there is with the strong acid. So anyway, just realize we'll see acetic acid a lot. I will abbreviate it HOAC, and I'll sometimes abbreviate acetate OAC minus. You're welcome to draw them out as the full molecular version too, which is fine, but it is a common thing and we'll use it here in the future. Now, strong bases, like strong acids, dissociate 100%. Sodium hydroxide is an example of a strong base. It breaks down 100% into sodium ions and hydroxide ions. If hydronium is the way that you know an acid is an acid, hydroxide is the way that you know a base is a base. So every time you see hydroxide, that basically means that you're starting with something basic. There are 3 strong monobasic systems that I would recommend knowing. Sodium hydroxide, potassium hydroxide, and lithium hydroxide. So like with the strong acids, there's going to be thousands of bases, but most of them are weak bases, okay? There's only 3 strong monobasic systems that you need to worry about. And in this class, then basically all the other bases will be weak. There are other strong bases, absolutely, just like there's other strong acids, but they're not as common, okay? We're looking at the most common ones. So if you know the 3 strong monobasic systems and the 5 strong monoacidic acids, you'll be good to go. Calcium hydroxide is an example of a strong dibasic system. And in a dibasic system, you have 2 hydroxides to donate. And this is another strong base. It's not one that you need to memorize because we won't use it as much. A dibasic system means that there are 2 hydroxides to donate. You can have diacidic or diprotic systems, sometimes they call them, when you have 2 H pluses. Anyway, there's lots of other ones, but again, if you know the 3 strong monobases and the 5 strong monoacids, honestly, you're good to go for this class. Calcium hydroxide is especially interesting because it forms from lime. If you add water to lime, calcium oxide, it makes slaked lime, which is this calcium hydroxide. It's a really interesting system. A weak base, then, is just a base, something that creates hydroxide, but it's much less than 100% ionized. And in these kind of systems, you would use an equilibrium symbol. And one of the best known weak bases is ammonia, NH3, which we've been dancing around. Ammonia doesn't have a hydroxide in the formula. There's no oxygen at all. But when it reacts with water, it can make hydroxide, and that's what makes it a base.
Ammonia acts as a base in solution by accepting a proton from a water molecule. This liberates a hydroxide ion and results in a basic solution.
Remember that ammonia is NH3 and ammonium is NH4 plus, and the difference between those is the addition of an H plus to it. So when ammonia is in water, it makes ammonium and hydroxide. The presence of hydroxide is enough then to make this system somewhat basic. Again, there's literally thousands of weak bases. You do not have to memorize them by any means. However, do remember that there are 3 strong bases we'll run into a lot, and then basically all the other bases will be weak. It is cool to know ammonia versus ammonium. We'll run into those just like acetic acid and acetate will run into. Keep those in the back of your mind. Scientists wondered what was up with acids and bases for a long time, and there are many acid-base theories out there, but the theory that's used the most is called the Bronsted acid-base theory or the Bronsted-Lowry theory. And Bronsted and Lowry, as I understand, were 2 scientists working in separate places that essentially came up with the same idea. Bronsted was the first one to propose it. Lowry had been working in the basement, but he had notes and stuff. So anyway, officially Bronsted-Lowry, but most people call it Bronsted. Doesn't matter. I think scientists like that little O with the circle in it. I really think that's part of it. But anyway, we're going to talk here about the Bronsted-Lowry theory or the Bronsted acid-base theory, and it's pretty chill. In the Bronsted theory, acids donate H plus ions and bases accept H plus ions. All right? So in the Bronsted theory, acids donate H plus and bases will accept the H pluses. And it's a pretty mellow thing, but with really good consequences for how these things all work out. So remember this, acids will give up the H plus and bases will accept the H plus. If we go back to the idea of ammonia, all right, ammonia is a base because it's accepting an H plus from water. And in the process, then you end up making ammonium and hydroxide. So in the Bronsted theory, it's not that the ammonia creates hydroxide, it's that the ammonia accepts an H plus from water. That's what makes it a Bronsted base. On the other hand, water is giving up an H plus to ammonia to make ammonium. So water here is acting as an acid. And that's kind of an interesting thing we'll talk about more here in a little bit.
Ammonia acts as a base in solution by accepting a proton from a water molecule. This liberates a hydroxide ion and results in a basic solution.
Because ammonia is a weak base, we're going to use the equilibrium, the double-sided arrows. And again, ammonia is accepting the H plus from water, so that means ammonia is a base. On the other hand, water is giving up the H plus to ammonia, so it's acting like an acid, no problem. And in the process, ammonium, NH4 plus, and hydroxide are made. However, this is equilibrium. You don't have to think just about left to right. You can think about right to left too, because that's what these things do. They're literally in flux. It's dynamic, all that kind of stuff. So if you think about ammonium and hydroxide as your quote-unquote reactants, making ammonia and water as products, look what happens. Ammonium is donating an H plus, so it's an acid, and that H plus is being accepted by hydroxide, so it's a base. You can think about these as acids and bases from either side, either direction, and that's going to be a really interesting part. Finally, before we leave this, notice that ammonia and ammonium are related by an H plus. All right, you give the H plus to NH3, it makes ammonium. You take away the H plus from NH4 plus, and it makes NH3. Also notice that water and hydroxide are the same way. There's an H plus between them. Water's giving up H plus to make hydroxide. Hydroxide's taking an H plus to make water. This is an important part of acid-base theory we're going to see here in a little bit. NH3, like we saw, is a base in water because NH3 is taking an H plus from water. That's what a Bronsted base is. Water here is acting as an acid. It's giving up an H plus to make hydroxide. And sometimes when people start learning this, they think, oh my gosh, water is acidic. They like spit their water out or something like that. So first of all, acids and bases for that matter can be bad when you would touch them or drink them or something like that. However, most of the foods we eat and drink are actually acidic. And most of the cleaners that we use in our houses, most of those are actually basic. So moderate levels of acid and base are totally fine for our bodies, all right? You don't have to spit out the water. We're going to see water has some other interesting properties here coming up in a little bit. But I want you to realize that acids and bases are just terms, and they're nothing to be feared. Our bodies have totally adjusted to moderate amounts of acid and base, and it's no problem at all. But we'll see here that water is especially interesting. A conjugate pair is a pair of chemicals related by an H+. So in the last slide, I mentioned how ammonia and ammonium are like related by an H+, and so are water and hydroxide. If you have two chemicals that are related by an H+, like one would give up the H+, and the other one would accept the H+, we're going to call them a conjugate pair. So ammonia and ammonium are a conjugate pair. One of them will be the base, the thing that takes the H+, and the other one will be the acid, the thing that gives up the H+. And if you're uncertain which is which, the species with more hydrogen will be the acid, and the species with less hydrogen will be the base. Water and hydroxide are also a conjugate pair. And we're going to see that every acid has a conjugate base, and every base has a conjugate acid. This is a real wild part of acid-base theory. And again, because this is equilibrium, we can think about it as going back and forth, back and forth. It's going to create some really interesting things coming out. Here's hydrogen carbonate. Hydrogen carbonate is a weak acid, all right? It reacts with water. It makes hydronium, because acids should be creating hydronium somewhere or another, just like bases will create hydroxide, and carbonate. But now what you can see is, you can see now where the conjugate pairs are, all right? And remember, a conjugate pair is always an acid and a base, and they're related by an H+. So hydrogen carbonate on the left and carbonate on the right, those are a conjugate pair. The hydrogen carbonate gives up the H+ to make, and the base will take the H+ to make hydrogen carbonate. Water and hydronium here are also a conjugate pair. Water here is going to take the H+ to make the hydronium, so that's when the water's acting like a base, and hydronium will give up an H+ to make water, so it's acting like an acid. Hopefully, though, you're seeing here that, whoa, water was an acid on the last screen when it was reacting with ammonia. Here, it's acting like a base. It's reacting with hydrogen carbonate to make hydronium. Water can be both an acid and a base. Here's a question you might run into. It says, which of the following is not an acid-base conjugate pair? Okay, and an acid and base conjugate pair is going to be related by an H+. So one of them will have an extra H+, and the other one will be missing an H+. We've already seen that E is a conjugate pair, nitric acid and nitrate. We saw that earlier. But anyway, you take away an H+ from nitric acid to make nitrate. You add an H+ to nitrate to make HNO3. And you can see that most of these are conjugate pairs. This one has two hydrogens and this one has one. That's carbonic acid on the left and hydrogen carbonate or carbonic acid on the right. HNO2 nitrous acid and the nitrite ion, that's another conjugate pair. Hydrofluoric acid, fluoride, etc. However, A up there, HClO and Cl minus. If you took an H plus from HClO, you would have ClO minus, the hypochlorite ion. And the hypochlorite ion is not the same as chloride. So A is not an example of a conjugate pair. You can't just add or subtract an H plus to make one into the other. Cl minus and HCl would be a conjugate pair, and HClO and ClO minus would be a conjugate pair, but that extra oxygen is enough to make them not conjugates. It's only plus or minus an H plus ion.
Without the addition of any other substances, two water molecules can interact with each other to produce a hydronium ion and a hydroxide ion by transfer of a proton from one water molecule to another. This process is called autoionization.
Water actually has acid and base in it at the same time. If you're drinking water, don't spit your water out, okay? It's good for you. It's totally normal. But anyway, water has what they call autoionization. Those strong hydrogen bonds in there are able to rip a hydrogen ion from one of the waters, making a hydronium and making then a hydroxide in the same place. Now, in normal water, you normally have just as much hydronium as you have hydroxide, and we're going to see it's not a lot, all right? But this is a process that occurs. Water can act as both an acid and a base, and this is only possible through this autoionization process. It's those strong hydrogen bonds, again, creating a really unique effect in water, which is really cool. People have studied this reaction quite a bit. And up there on the top under autoionization, you've got two water molecules in equilibrium with hydroxide and hydronium. Remember, hydroxide is the active part of a base, and hydronium is the active part of an acid. So people have studied this reaction. Now remember, you don't include liquids and solids in equilibrium. So Kw is a type of equilibrium constant expression. And just like all equilibriums, it's products over reactants. We would have the hydronium ion times the hydroxide ion in the top part, but in the bottom part, because water as a liquid is the only playing species, in which you don't put in K expressions, you would just have divided by 1. So Kw equals hydronium times hydroxide. At 25 degrees Celsius, Kw has been measured to be 1.00 times 10 to the minus 14th. And that's really less than 1. All right, this is a very reactant-favored reaction. And what that tells you right now, I'm hoping that you're seeing, is that, wow, there's not a lot of hydronium and hydroxide in normal water. All right, it's going to be a really small part. Most of the chemicals in this reaction are going to be liquid water. All right, you only have a very small amount of hydroxide and hydronium running around. In a neutral solution, you should have then just as much hydronium as you have hydroxide. And we want to drink neutral water, right? We don't want to drink water with an excess of acid or an excess of base. So if hydronium and hydroxide are equal, then Kw, which equals hydronium times hydroxide, is basically equal to hydronium squared or hydroxide squared, because it's going to be the same thing in a neutral solution. So if that's the same, Kw, that 1.00 times 10 to the minus 14th, equals essentially x squared. So you can solve for x, the concentration of hydronium or hydroxide, 1.00 times 10 to the minus 7th moles per liter. Now, let's think about that number. That's the amount of acid and the amount of base in normal water at 25 degrees Celsius. And if you've watched the concentrations that we've used in the labs and we've talked about, a 10 to the minus 7th moles per liter is very small, all right? That's not a lot of acid and base. And this is an amount of acid and base which our bodies are used to. We can accept a 10 to the minus 7th moles per liter acid or base without harm to our bodies. All right, it won't burn on the way down or anything like that. So this hopefully makes you feel good then about drinking water, which you should do anyway. It's a very small amount. Now, Believe it or not, of all Chem 223, this 1.00 times 10 to the minus 14th number is going to be super important. A lot of the equations we're going to talk about are based on kW, so you really need to know / memorize this number. But I also want to put a warning in. In future lectures, I'm just going to start going crazy here with kW. You'll see all this stuff we're going to do. It's fantastic. But officially, kW is only effective at 25 degrees Celsius. And K, like all equilibrium constants, is temperature dependent. If you're doing acid and base studies in like a human being in the body, the normal body is about 37-ish degrees Celsius. It's warmer than 25 degrees Celsius. And some of the acid-base expressions we're going to talk about may need to be altered a little bit to adjust for the new temperature, because K will change with temperature. And in the body, some of the things we'll talk about may not be quite as accurate. However, overall, most things are done at 25 degrees Celsius, and everything we'll talk about will be pretty effective. But I just want to know, if you're doing medical research, you may want to reconsider some of the things we're going to talk about for your system. You would get a different value of kW and go from there. It's kind of an interesting thing. But most acid-base reactions are done at room temperature, which makes this all really effective. So here's a solution. A solution has a hydronium of 1.0 times 10 to the minus 8th moles per liter. And the question is, what is the hydroxide ion equal to? Good question. All right. This is the first time now that kW is going to be helpful, because kW equals hydronium times hydroxide. And we've got the hydronium value there. And if you know what kW is, and that's a pretty sloppy W, I apologize. But anyway, that kW is the 1.00 times 10 to the minus 14th. So to solve this problem, you want to solve for hydroxide. kW, 1.00 10 to the minus 14th, divided by 1.0 times 10 to the minus 8th. That's going to be the way to find hydroxide. If you do that in your calculator, that comes out to be 1.0 times 10 to the minus 6. So this is the kind of thing that you can use kW for, and there's lots of uses for this, but you do need to know the 1.0 times 10 to the minus 14th number. Cool for school. So calculating the amount of acid and base, i.e. calculating the hydronium hydroxide, is going to be really important. This is the kind of question you might run into. Let's say that you add 0.0010 moles of sodium hydroxide to a liter of pure water. We can use this information to calculate the hydronium and the hydroxide. So what we'll do to figure this problem out is we'll go back to the equilibria with kW. And remember, that was 2 waters as liquid in equilibrium with hydronium and hydroxide, and kW was equal to hydronium times hydroxide, etc., etc. We can use Le Chatelier's principle here to do some kind of predictive natures as to how these questions are going to turn out. If we add sodium hydroxide, honestly, we don't care about this sodium. We want to know what's going to happen as we add hydroxide. Well, if you add hydroxide to this equilibrium, which is what this is, hydroxide, a product, we're adding a product, it's going to shift this reaction to the left, all right? Remember, as you add something, in Le Chatelier's principle, it tends to move to the opposite side. We're adding a product, this should make the equilibrium move more towards the reactant side. So the hydronium concentration will go down as we add a base. And that kind of makes sense intuitively, right? Because hydroxide is a base, bases and acids are like cats and dogs, they're really reactive. You add hydroxide, your hydronium should go down. Hydronium will be less than 10 to the minus 7th moles per liter at equilibrium. Hydronium and hydroxide equal 10 to the minus 7 when they're by themselves. But if you add hydroxide, it's going to shift it to the left. Your hydronium concentration should be less than 10 to the minus 7th. So what we can do here is set up another ICE table, all right? ICE again stands for for initial change in equilibrium. We don't need the water because liquids and solids are exempt from equilibria, but of course we do need hydronium and hydroxide. So the way I would do this is to think about the hydroxide as initially we've got 0.0010 moles per liter going in, and the hydronium initially is 0. Now, in the Kw expression, hydronium and hydroxide will be non-zero numbers, and as the water breaks down, it will make X amount of hydronium and X amount of hydroxide. So at equilibrium, hydronium will be X, hydroxide 0.0010 plus X. And knowing those values at equilibrium, we can set them equal to Kw, 1.00 times 10 to the minus 14th. So Kw equals X times, parentheses, 0.0010 plus X. In an equation like this one right here, all right, if we were going to set this up, you could write this out, and it would be X times both of the pieces inside, which would be X squared plus 0.0010X, and you could put Kw on the other side, and this would be a quadratic formula. All right, you'd have X squared term, you'd have an X term, the number would be the Kw, all right, and there's nothing wrong with solving it that way. However, you can also use common sense a little bit to make your life a lot easier. Now remember, before the hydroxide was added to the water, X, the hydronium and hydroxide, was 10 to the minus 7. 10 to the minus 3, which is what 0.0010 is. 10 to the minus 3 plus 10 to the minus 7th, which is what you would have had under pure water. The 10 to the minus 3 is so much bigger than the 10 to the minus 7, you can basically ignore it. Like mathematically, put 0.0010 plus 10 to the minus 7th. And to any kind of sig figs, especially the ones we're dealing with here, the answer will be 0.0010. It's like if you had, say, 1,000 pieces and you added one more. It's probably not going to make a big difference if you have 1,001, maybe if it was a gold bar or something, but normally having an extra piece with that many, it's not a big deal, all right? In science, believe it or not, significant figures can be your friend. So instead of having a quadratic formula, which you could solve for, you can actually just say, hey, this little plus x here, it's going to be pretty small. And if it is pretty small, it makes your life a lot easier, because instead of having an x squared and a 0.001x, you can cross that part out, and Kw equals 0.0010 times x. So if you do that, your life is a heck of a lot easier. Instead of having a quadratic, you can abbreviate it as Kw equals x times 0.0010. Now remember, X is hydronium here, so let's put hydronium back in. Kw divided by 0.0010 will be your hydronium. 1.0 times 10 to the minus 11th is the answer. Now, if you're feeling weird about making these kind of assumptions, you can always take the answer here, 10 to the minus 11th, and put it back up here. Does it make a big difference on the hydroxide? We were talking about 0.0010 plus a 10 to the minus 7th number. The number we calculated is even smaller. It's 1.0 times 10 to the minus 11th. And 0.0010, a 10 to the minus 3 number, plus a 10 to the minus 11th, it's going to be like, 100 million plus 1. It doesn't make any difference. That extra 1 is not a big deal. With sig figs here, we're limited to the 10th, 100th, and we're limited to the 0.0010 position right there. All right, that would be the 10,000th position. And that's where we have to cut the sig figs off. And a 10 to the minus 11 plus that number is still going to be 0.0010. So for all of these reasons, I do recommend starting to think about when you can cut out little x, because you don't have to go to quadratics or anything like that. And even if you use the cool solve function on your calculators, which I did encourage in the last section, it's going to take you longer to put in those numbers in your calculator to hit solve than if you do it this way. And you're going to get the same result almost all the time. So this is something we'll start talking about when you can sometimes pull out a plus x. And if you do, it makes your life easier. I am the lazy chemist, but all I'm trying to do here is save you some time. When you have 0.0010 mole of sodium hydroxide, the hydronium goes from 10 to the minus 7th in neutral water to 10 to the minus 11th moles per liter. And of course, that's pretty small. This solution would be considered basic, all right? Your hydronium, 10 to the minus 11th, is so much smaller than the 10 to the minus 3 moles per liter hydroxide. And anytime you have more hydroxide than hydronium, we would consider this number to be basic. If the hydronium value was larger than hydroxide, that's when we would consider it to be acidic. But in this case, more base than acid, this is going to be basic. Now, using 10 to the minus whatever numbers is kind of unwieldy sometimes. So instead of using that, we use the pH scale. And pH is just a more common sense kind of number, which you can then figure out quickly if something is acidic or basic. The pH scale supposedly was developed by Soren Sorensen. Again, another cool person with the O's with the lines through the middle of it. The P stands for potential, supposedly. So pH is the potential of the hydrogen ion to do things. Anyway, pH is equal to minus log of the hydronium concentration. So the number you calculated in the last slide, you could plug this into pH expression to see what the pH is. Now, in a neutral solution, like we saw earlier, hydronium and hydroxide are both equal to 10 to the minus 7th moles per liter at room temperature. So the way that people get the pH of a neutral solution minus log of that number, pH equals 7. So pH will equal 7 for neutral solutions. But realize now that in a neutral solution, it's not that you don't have any acid and base, it's just that the amount of acid equals the amount of base. And they're really small amounts, so they don't really interact with each other. However, there is both acid and base in there, and that's something kind of interesting. So if I said you had a pH of 7, you'll know instantly that it's neutral now, because pH of 7 is the neutrality point in pH. On the other hand, if I said, well, I had a hydronium of 1.00 times 10 to the minus 7th, it's going to take a little bit longer to process what that means and to think about if it's acidic or basic. So this is just one kind of cool technique that scientists use. The pH scale, super helpful for instantly telling if something is acidic or basic or neutral. The 0.0010 molar sodium hydroxide solution, we can calculate the pH, and what the heck, let's do that. We saw the hydronium was a 10 to the minus 11th number, so pH minus log of 1.0 times 10 to the minus 11th, this pH comes out to be 11, all right, 11.00. And again, pHs that are larger than 7 are the ones that are going to be basic. So basic solutions, first of all, will have a pH larger than 7, and having a basic solution just means that the hydroxide, this number, is larger than the hydronium, this number. You have more hydroxide than you have hydronium. An acidic solution, you'd have the reverse case. In an acidic solution, you'd have more hydronium than you have hydroxide, and your pH values will be less than 7. And then neutrality just means that your pH is equal to 7. The acid and base quantities are equal. Depending on the situation, sometimes pHs can be about 7 to be considered neutral. It kind of is in a case-by-case basis, but realize that pure 7 would be the pure neutrality point, and you can go from there. If you have a solution with a pH of 10.5, how would we describe it? And the answers are acidic, basic, neutral, and lame. Lame could be the answer, I won't deny it, but let's try and keep our science hats on here for a little bit. The pH number will tell you which one it is, and of course, pH is larger than 7, those are going to be considered basic. All right, so quickly you can tell if something is acidic, basic, or neutral. Acidic would be numbers less than 7, neutral would be equal to 7, or very, very, very close to 7, etc., etc. And they still could be lame, but that's not really where we're talking about now. Oh well. You can find the pH of a lot of things around you. I used to drink a lot of Diet Coke. You can put a pH probe, which is what that thing is there in the lower right corner. You can put a pH probe in Diet Coke or beer or wine or water or anything you want to and stuff, and you'll get the pH. pH probes are pretty cool. If we're doing face-to-face labs, we'll use a pH probe to find the pH of a solution. But anyway, you put the pH probe in your Diet Coke, the pH comes out to be 3.12. Well, in this case, then, your Diet Coke would be considered acidic because the pH is less than 7. That means more hydronium relative to hydroxide. Most of the things we eat and drink are somewhat acidic. How much acid is there, Dr. Russell? Great questions, random student in the back of the room. Let's figure it out. So pH equals minus log of the hydronium. So if you want to know how much hydronium, how much acid, moles per liter there would be, let's deconstruct that 3.12. We'll put 3.12 in for pH, and we'll solve for hydronium. Now, this is a base 10 log, log, and it's super important that you use base 10 log and not the natural log, ln. You'll get different numbers here, so make sure that your logarithm is log. And I highly encourage you to go through some of these examples to make sure that you're getting these numbers. So log of hydronium equals minus pH if you put the negative on the other side. The anti-log is the way to get rid of that log, and the anti-log for a base 10 log, it's 10 to the x. This is just math fun, and you don't have to be an expert in logarithms to make this happen. But on your calculator, there's often an log button, and then second function log on your calculator, it usually has a little 10 to the x. That's the anti-log, all right? So if you wanted to find the amount of hydronium, you would take the anti-log of both sides. Hydronium equals 10 to the minus pH. So it's like 10 raised to the power of log hydronium equals 10 raised to the power of minus pH. The 10 and the base 10 logs cancel out, so that's where hydronium comes from. And then on the other side, you have 10 raised to the power of minus pH. Now, anti-logs are pretty chill. 10 little caret if you want, minus 3.12, or if you have the number, you can do it. You should get 7.6 times 10 to the minus 4 moles per liter. So when I used to drink Diet Coke, then I would be drinking a 7.6 times 10 to the minus 4 molar acidic solution. Oh, joy. A solution has a pH of 4.50. The hydronium concentration is, and you can figure it out. Okay, so this is going just like in the last example from a pH to a hydronium. As we saw, hydronium is 10 raised to the power of negative 4.50. So again, this is something to do in your calculators. And if you do that, it comes out to be answer B, 3.2 times 10 to the minus 5. So this is how you can figure out hydroniums from pH. And again, if you went minus log 3.2 times 10 to the minus 5, you should get an answer of 4.50. If you are a person that's interested in significant figures, some of the numbers I've used recently maybe haven't made a lot of sense. So I want to talk here about how to figure out significant figures from logarithms. And I'm going to try in Chem 223 to be a little bit mellow when it comes to sig figs. In earlier classes, I was tenacious and I was always after you for doing sig figs. Logarithms are a little bit weird. I recognize it, but I also want you to understand where the numbers come from. I'd like you to have an approximate appreciation for how to do this. The more, of course, you follow it, the better and stuff and see. So when it comes to significant figures and logarithms, all right, logarithms are really just exponents with special significant figure rules applied. And in general, the log of an experimentally measured number with n sig figs gives numbers with n decimal places after the decimal, all right? So this is a little bit weird, but let's say you're taking a number with a molarity of 3.2 times 10 to the minus 4. Well, 3.2 means that would be 2 sig figs. That's the n would be 2. And if you're going to take the log of that number, you might get, who knows, knows what kind of number, but your reported value should have two numbers past the decimal point, all right? That's what it means when it says n decimal places after the decimal. So if you have two sig figs, you would have something point something something. And the something something after the dot, that would show you number of sig figs. Now, if that's as clear as mud, I apologize. Let's look at some examples. The first one here, log 3.07 times 10 to the minus 3. So this is a 3 sig fig number, 3.07. We don't include the exponents. So the answer here, we would have 3 sig figs past the decimal. All right, 3 numbers past the decimal. The 2 there is somehow related to the power of 10, the 10 to the minus 3. That's the way I think about it, all right? So 3 sig figs in means 3 sig figs past the decimal. Log of 1.1 times 10 to the minus 8, that's a 2 sig fig number again. So we would have 2 digits past the decimal. So that would be 7.96. Now look, it looks like you're going from 2 sig figs to 3 sig figs, 7.96. But in these logarithms world, the 7 just tells you the power of 10 to use. So scientists then don't look at that number for sig figs. We would look at the 0.96. And this definitely becomes important if you do an anti-log, an anti-natural log, or an anti-base 10 log. 10 raised to the power of negative 3.12. This is the anti-logarithm function. And so in this case, we want to convert this number, this pH-like number, back to a regular. 2 numbers past the decimal means 2 sig figs in the final answer. So this gets a little strange, but you can see here we went from what looks like a 3 sig fig to a 2 sig fig. But again, the only digits that count are the numbers past the decimal when you're dealing with logarithms, all right? So this is a little bit weird. I totally understand, but that's going to be the basis for a lot of the calculations you're going to see in these sections. And again, if you have questions on this, let me know. Try to use reasonable significant figures in your answers. If you use these rules, that's of course the best, all right? But they can be a little bit weird. Just try not to go crazy on me on sig figs, all right? The substances around us definitely have pH values, and again, most of the time the things we eat and drink are somewhat acidic, and the things that we use for cleaners oftentimes are basic. Blood is kind of in the middle. Blood pH changes a little bit, but you can see it's usually a little bit basic, and that's kind of cool. So quickly, by seeing those numbers like pH of 3.8 for the orange, you know that that's acidic. On the other hand, pH of 11 for ammonia, that would be very basic. Don't be trying to eat and drink basic things by default. Our bodies are more set up for acidic things than basic things. Sorensen, when he developed the pH scale, it was actually kind of a broader thing than just pH. You can have a px scale for any quantity x. So px equals minus log of x. So the potential of the x ion equals minus log of the concentration of the x ion. It's kind of cool, and we're going to use this. pKa is something we'll use here coming up, and I haven't talked about Ka yet, but I do want you to see that pKa equals minus log of Ka. So instead of this x, we're putting Ka in. I'll talk about what Ka is here a little bit, but just realize pKa equals minus log of the Ka. POH is another thing we're going to talk about soon. POH equals minus log of the hydroxide ion. So if you have so much hydroxide ion, minus log of that number will give you the POH scale. Kw equals hydronium times hydroxide, and it equals 1.00 times 10 to the minus 14th at that almost magical room temperature, 25 degrees Celsius. There's some interesting things you can do with this expression right here. Minus log of hydronium is pH, minus log of hydroxide is POH. In the world of logarithms, if you go minus log hydronium times hydroxide, you can actually break that up. you can break up minus log hydronium times hydroxide into minus log hydronium plus minus log of hydroxide. This is a reason why people like using logarithms in science. And that equals then minus log of Kw minus log of 10 to the minus 14th. Minus log of 10 to the minus 14th is just 14. And minus log of hydronium is pH. And minus log of hydroxide is POH. Lo and behold, 14 equals pH plus POH is going to be something pretty important. If you have pH, you can quickly find POH. If you have POH, you can quickly find pH. It comes from the Kw expression, equals hydronium times hydroxide, but sometimes it's more helpful to think about it in pH versus POH than hydronium and hydroxide. That weird pKa thing up there that I mentioned, there's also a pKb, and you can probably imagine that the big K is an equilibrium constant, yes, and the little a and the little b stands for acid and base, also yes. When we talk about pKa and Ka and pKb and Kb, we're going to see that 14 equals pKa plus pKb, and we'll talk about that later, so just hang on. But for right now, what I want you to see is 14 equals pH plus POH. Again, that's for room temperature. If you do other temperatures, it may not be equal to 14, it'd be somewhat different. Also realize that there is a PKA Kickboxing Association, Professional Kickboxers of America, something like that, but that's different than the PKA we're going to talk about. Sorry about that. A solution has a hydronium ion concentration of 3.2 times 10 to the minus 5 moles per liter. What is the POH? Okay, so there's a couple different ways that you can do this problem, all right? So hydronium is the H3O plus, and we want to somehow get a POH out of it. And so one way to do this would be to use Kw. Kw equals hydronium, that number, times hydroxide. You could solve for hydroxide, and then minus log of hydroxide would give you the POH. Another way to do this is you could figure out pH of the hydronium. pH equals minus log 3.2 times 10 to the minus 5. And then whatever pH is, 14 minus pH would give you POH. So either way you do this is fine. In this problem, it looks like what I did was something totally different. POH equals minus log of hydroxide, and hydroxide is Kw divided by hydronium. So I plugged all those pieces in there to get 9.51. All of these ways are fine, and you pick the one which works best for you. That's what's really important. As long as you can get the 9.51 answer, I'm very, very pleased. Litmus paper is a way in a chemistry lab that you can quickly tell if something is acidic or basic. And there's different kinds of litmus paper, but these litmus papers here turn a little bit more reddish orange, or I guess it's more orange color if it's acidic, and a little bit more blue or that dark purple there if it's basic. And the amount of acid and base will make a big difference. Now, in this lecture so far, we've talked about pH and hydronium, and we've also made some connections with POH and hydroxide. And we're going to use all four of these quite a bit here. So let's talk about pH first. We saw that pH usually goes from 0 to 14 and neutrality is 7. And that comes from the fact that hydronium and hydroxide are both equal to 10 to the minus 7 if it's neutral. But in a basic solution, you're going to have more hydroxide than you would have hydronium. And in an acidic solution, you'd have more acid than you would have base. So in an acidic solution, your pHs will be closer to 0, definitely greater than 7, closer to 0, depending on how much acid there are. And the concentration of the moles per liter, if you will, of hydronium will be a number which approaches 1. All right, I have moles per liter of 1 mole per liter would be a pH of 0. So it'll be some number between 10 to the minus 7 and 1. Now, as hydronium goes up, hydroxide goes down. Kw equals hydronium times hydroxide. So if you have a hydronium of 1, your hydroxide is going to be very small. So notice that as the acid amount is getting bigger, the base amount is getting smaller, all right? As hydronium goes from 10 to the minus 14 to 1, the hydroxide goes from 1 to 10 to the minus 14. 14. What this means is that as hydronium goes up, the hydroxide goes down, because both of those together must equal Kw. But here's where it gets a little weird. As the acid goes up, the pH goes down. It goes from 14 basic to 0 acidic. So hydronium goes up and pH goes down. On the other hand, POH, which is a reflection of base here, POH is going to get bigger as the acid gets bigger too, all right? The hydroxide is decreasing as the acid goes up, so that means the POH is increasing. So what I want you to do in this slide is just take a minute and think about these relationships, all right? Because in an acidic solution, you're going to have a low pH, because pH will go to 0 as it gets acidic. And in an acidic solution, that means you have a high amount of hydronium. But high amount of hydronium means low amount of hydroxide. Hydronium times hydroxide, remember, equals Kw. Low amount of hydroxide, high POH. So notice this back and forth kind of thing. So again, acidic solutions, low pH but high hydronium. High hydronium means low hydroxide. Low hydroxide means high POH. Think about this in your mind. Get this clear. It makes your life a lot easier. In basic solutions, it's the opposite. In a basic solution, you would have a high pH. It would be larger than 7. And basic solutions means your hydroxide will be higher. That means your hydronium will be lower. But high hydroxide, small POH. POH is going to be smaller. Just like acidic solutions have small pHs, basic solutions have small pOHs. So this up, down kind of thing is something you really got to get clear in your head to figure this out. It's not hard. Just kind of go through it. You can always put in random numbers. So like put in a pH of 3 and figure out what hydronium, hydroxide, and POH is. You can do the same thing with basic solutions. Put in a pH of 10 or something. Figure out what hydronium, hydroxide, POH. You can see it that way too. All these weak acids and weak bases do have equilibrium. And we talked about conjugates, how conjugates are related by an H plus back and forth. We're going to look now more about those equilibria and see some of the things you can get. So this is 3 sets of conjugates. And again, conjugates are just related by plus or minus H plus. The acid will have more hydrogens, the bases will have less. So acetic acid has more hydrogens than the acetate. Ammonium has more hydrogens than ammonia. Hydrogen carbonate, more hydrogens than carbonate. All of these acids and bases don't ionize very much. They won't make a lot of hydronium or hydroxide. It's usually less than 5%, sometimes a lot less than 5%. So unlike, say, HCl, a strong acid, which 1 mole of HCl makes 1 mole of hydronium, these acids, like ammonium, you have 1 mole of ammonium, you might only have something like 0.0001 moles of hydronium. You don't have the ionization in weak systems that you do in strong systems. This is the example with acetic acid. Acetic acid reacts with water. It makes hydronium. It's an acid, and the conjugate base. All right. Now remember that acids always make hydronium. That's the thing that makes acids and acids. Water here is acting as a base, and the conjugate acid of that would be hydronium, just like the conjugate base of acetic acid would be the acetate ion. Ka, which I babbled about a little bit earlier, Ka is an equilibrium constant, a K, and it's an acid-based equilibrium constant. And for this reaction, remembering that water is a liquid and we keep liquids and solids out, Ka equals hydronium times the conjugate base concentration divided by the acetic acid concentration. And this has actually been a well-studied system. Ka 1.8 times 10 to the minus 5. Remembering that equilibrium constants less than 1 are very reactant favored, this is definitely a weak acid because K less than 1, most of this is going to be on the reactant side. There won't be a lot of products here. All Kas, for our purposes, will be numbers less than 1. Sometimes they'll be equal to 1, and if they go larger than 1, we'll just say very large. You'll see why in a little bit. But this is the form of Ka. Ka equals hydronium times conjugate base divided by the weak acid. And again, because the weak acid doesn't 100% break down, you will have some weak acid around. You'll also have some conjugate base around. It's all related by the hydronium right there. So Ka is an acid dissociation constant. It's mostly used for weak acids. And the form of these Kas is always the same. It's acid plus water making hydronium and the conjugate base. So Ka equals hydronium times acetate divided by the acid itself. And again, the Ks we're going to look at here are very, very small. Here's a generic representation for some random HA acid. And again, we don't put liquids and solids in, so water is excluded. Hydronium times the conjugate base divided by the acids. Weak acids have Kas that are less than 1, and because K is less than 1, that means you have a very reactant-favored system. You won't have a lot of hydronium because hydronium is a product. pHs usually run in the range 2 to 7, all right? They have to be acidic, so 7 would be neutral, so it's probably going to be a little less than 7. However, most of the time, because you don't have a lot of hydronium, pHs won't get any lower than 2, and that's a rough thing, and I'm sure there's exceptions and stuff like that. A weak base has a Kb associated constant with it, just like Kas for acid. Now with a base, bases react with water. They make a conjugate acid, which I've written there as BH+, and hydroxide. So bases make hydroxide, and acids make hydronium. Kbs then have hydroxide in them. But you can see that once again, K is less than 1. We're going to see values of them here. That means a lot of reactant, not a lot of product. We won't have a lot of hydroxide here. The pHs won't be as basic as things like sodium hydroxide. So these pHs tend to run in the range of like 12 down to just above 7 a little bit, depends on the base. But again, all of this is just because these bases don't dissociate very much into hydroxide, so you don't get the same kind of kick. So Ka is an acid dissociation constant, and Kb is a basic dissociation constant. And they're very useful when you have weak acids and weak bases. So HA, the random acid plus water, makes hydronium plus the conjugate base, A-. That's the Ka expression. Now, let's remember here that A- can also be a base. So let's write now A- as a base. A-, the conjugate base, is a base in its own right, and it will react with water to make conjugate acid and some hydroxide. This is what Kb means. Now, if you look at these two expressions, you might know where we're going. Because we have HA on both sides, we've got A- on both sides. So let's combine those two expressions, and let's see what's left off. And if you do that, the Kas will combine, the A- will cancel, the HAs will cancel. You'll have two waters. 2 waters equals hydronium plus hydroxide. Guess what? That's Kw. Kw is hydronium times hydroxide. And we got that same expression by multiplying Ka times Kb. Remember, if you add equations together, you can multiply the Ks to get the overall K. This is just Kw. So why I bring this out is that if you have a weak acid and it's Ka and its conjugate base with its Kb, Ka times Kb, if they're conjugates, will equal Kw. And that's a really cool relationship. We're going to see lots of uses for that. Now, you have to have them be conjugates, all right? So like acetic acid and acetate, or ammonia and ammonium. Those kind of Kas times Kbs would equal Kw. But you couldn't use, for example, like acetic acid and ammonium. Those are acids and bases, but they're not conjugates of each other. They must be conjugates for this to be effect. Now, just like hydronium times hydroxide equals Kw, and we saw that pH plus POH equals 14, you can do the same kind of thing here for the Ka times Kb. And if you do it, then you get pKa plus pKb equals 14. We will use this a lot, as well as pH plus POH equals 14, as we go through the next several lecture sections. This is a table of acids and bases, and this is one that's actually in problem set 2, and I believe problem set 3 as well. None of these numbers are numbers you have to memorize, but I'd like to talk about the organization of things like this. So first of all, there's all kinds of acids listed on the far left, and a whole bunch of bases listed on the far right. If you start with the acids in the upper left corner, you can see that there's a couple of the really strong ones: perchloric, hydrochloric, nitric acid. Those are some of the super strong acids. And when you look at their Ka, it just says large, all right? That means that we really don't worry about Ks for strong acids. They're so product favored, it's almost like there's no reactant left over, so don't worry. Hydronium is equal to 1. That's the Ka. That's kind of the base that all these things will go on. And then you have a whole bunch of weak acids. And these weak acids go from biggest Ka to smallest Ka. So you can see that sulfurous acid there, H2SO3, 1.2 times 10 to the minus 2. And then you keep going down. There's 10 to the minus 4, 10 to the minus 5. So Kas are getting smaller as you go down. Well, if you think about what K means, as Ks get bigger, you have more product. And more product for an acid means more hydronium, more H3O+. So as Ka gets bigger, you're going to have more hydronium, more acid. That's going to make for a stronger acid. So the strongest acids are listed in the upper left corner, and the acids get weaker as you go down. So if you go down to the very bottom down there's like ethanol, which is basically not an acid. It's like so weak. Hydrogen, ammonia. Ammonia can actually be an acid, but it's so weak that nobody thinks about it. Because hydronium times hydroxide equals Kw, and because Ka times Kb equals Kw, on the other side we have the bases. But the base strength is biggest on the bottom, and it gets weaker as you go up. Because Kb is getting bigger as you go down on the right. Bigger Kb's mean more hydroxide, more base strength, if you will, and the weakest bases are up here. So this is a really cool kind of effect. And notice that conjugates are right across from each other. So there is HF, which is a weak acid, and there's fluoride. The conjugates are literally right across. If you multiply that Ka by the Kb for fluoride, it should give you Kw. And that should work all the way up and down. So the acids are getting stronger as you go up the chart. The bases are getting stronger as you go down the chart. And this is kind of how this stuff rolls. It's a little bit weird, but this is why this chart is done this way. We're going to use these Kas and Kbs a lot, all right? And I'll use these values in upcoming problems. There's nothing wrong with Googling Ka and Kb values, which you can find, but your numbers might be a little different than some of the ones we're going to use, just FYI. So this chart is going to be something you'll want to hold on to and compare. Here are 5 bases, and they all have a Kb value. And the question is, which one is the strongest base? Well, all of these Kb values are equilibrium constants. And as we saw in the last section, Ks greater than 1 have lots of product, Ks less than 1 have mostly reactant. So in this case, strongest base means most hydroxide, and hydroxide is a product. So to answer this question, we want the largest Kb value, because the largest Kb will have the most product. Most product means most hydroxide, and most hydroxide means strongest base. So if you look at those numbers right there, it looks like carbonate is going to be the strongest base. The strongest base is the biggest Kb. 2.1 times 10 to the minus 4 is bigger than all those other numbers right there. So that means carbonate will have the most hydroxide of all of those bases. Now, carbonate is still a weak base, and compared to like sodium hydroxide, carbonate will pale. It's not going to be able to compete. But of those bases up there, that would be the strongest base. You could do the same kind of things with Kas. Biggest Ka would be strongest, i.e. most hydronium. It's kind of cool how this works out. So it's actually able to classify acids and bases by strength. And again, strength just means most hydroxide for a base, most hydronium for an acid.